This video covers few important numericals from the chapter Chemical Kinetics. Before we go into the numericals, there are certain formulas that need to be remembered. So these are the formulas to be remembered. We have half-life of a zero order reaction, that is T half is equal to R naught by 2K. Half-life of a first order reaction, T half is equal to 0.693 by K. Rate constant of a zero order reaction, that is K equal to R naught minus R divided by T. Rate constant of first order reaction, K equal to 2.303 by T into log of R naught divided by R. Then we have the Arrhenius equation. Arrhenius equation can be written as K equal to A into e to the power of minus EA by RT. When we apply log on both sides, the formula takes the form log K equal to log A minus EA by 2.303 RT. So these formulas are also used in the numerical session. So now we'll go into the numerical session one by one. Question number 1. The rate constant for a first order reaction is 60 per second. How much time will it take to reduce the initial concentration of the reactant to its 1/16th value? So what is given here? The rate constant. Rate constant means K. K is 60 per second. How much time will it take to reduce the initial concentration of the reaction to its 1/16th value? So the initial concentration, let us take it as R naught, and the final concentration is 1/16th of R naught. We need to find the time taken to reduce the concentration to 1/16th of the initial concentration. We have the formula K equal to 2.303 by T log R naught by R. So we can take this T to LHS. So T equal to 2.303 by K log R naught by R. Now let us substitute the values of K, R naught and R. So T equal to 2.303 divided by T is 60 log R naught, we take it as R naught itself, divided by R, we take it as 1/16th of R naught. So R naught and R naught will get cancelled, or log 4 square can be written as 2 log 4. We can get the value of log 4 using the log table. We take the value as 40. 40 log 40 is 6021, 0th column and 40th row. So it is 6021. So 0.076 into log 4 is 0.6021. So the value of log 4 is 0.6021, and T equal to 4.6 into 10 to the power of minus 2 seconds. This is the answer. For a first order reaction, the rate constant is 0.1 per second. How much time will it take to reduce the concentration from initial value of 0.6 mole inverse to 0.06 mole liter inverse? So what is given? The rate constant is given. So K is 0.1 per second. Again, here we need to calculate the time taken to reduce the concentration from 0.6 to 0.06. R naught is 0.6, R is 0.06. Directly substitute the value in this formula. K, we know the value of K, that is 0.1. Log R naught is 0.6 divided by R is 0.06. So T equal to 23.03 log 10. Log 10 is nothing but 1. Substituting the values for log 10, we get the answer for the time taken is 23.03 seconds. Next question. For a first order reaction, show that time required for 99% completion is twice the time required for the completion of 90% of the reaction. We need to prove that the time required for 99% completion is 2 times the time required for completion of 90% of reaction. Formula for rate constant of the first order reaction is given by T equal to 2.303 by K log R naught by R. Here we have two cases. First, we need to calculate the time required for 99% of completion. And second, we need to calculate the time required for 90% of completion. So first, we'll calculate the time required for 99% of completion. For 99% of completion, the initial concentration is 100, and after 99% completion, the concentration remaining is 100 minus 99, that is 1. So your R naught is 100 and R is 1. Substituting the values for R naught and R, we get T 99% equal to 2.303 by K log 100 by 1. Log 100 by 1 is log 100 and log 100 value is 2. So T 99% equal to 2.303 by K into 2. Let us consider this as 1. Now we'll calculate the time required for 90% completion. Here also the initial concentration is, if it is 100, then the final concentration, the concentration remaining after 90% completion is 10. 100 minus 90 equal to 10. Substituting, this will be your R naught, this is R. So substituting the values for R naught and R, 2.303 by K log 100 by 10, that is log 10. Log 10 is 1. Let us put this as number 2. Now dividing 1 divided by 2, T 99% by T 90% equal to 2.303 by K into 2 divided by 2.303 divided by K into 1. So this both gets cancelled. Remaining is 2 by 1. So T 99% by T 90% equal to 2 by 1, or T 99% equal to 2 times T 90%. Hence proved. Question number 4. The rate of a reaction quadruples when the temperature changes from 293 K to 313 K. Calculate the EA, activation energy of the reaction, assuming that it does not change with temperature. So what is given? The rate of the reaction quadruples. Quadruples means the rate will become 4. Quadruples means increases 4 times. So if K1 is 1, K2 will be 4 times, that is 4. When the temperature changes from 293 K to 313 K. So T1 and T2 is given. K1, if it is 1, K2 is 4. Calculate the activation energy EA. So we know the formula to find the activation energy, that is log K2 by K1 equal to EA divided by 2.303 R T2 minus T1 by T1 T2. This R value is a constant value. Sometimes they may give in exam, or else you need to remember this value. R is 8.314, it is the standard value. Substituting, log K2 is 4, 4 by 1 equal to EA divided by 2.303 into R value is 8.314 into T2 minus T1, 313 minus 293 by 313 into 293. Log 4 by 1 is log 4 equal to EA divided by, multiplying this we get 19.14. On solving this we get 20 by 91709. Log 4 can be found using the log table. Log 4 can be taken as log 40, and we can see that log 40 in the 0th column is 6021. So we should write this as 0.6021. Log 4 is 0.6021. So log 4 is 0.6021 equal to EA divided by 19.14 into 0.000218. On solving, you get the value of activation energy, which is equal to 52.862 kilojoule per mole. This is the answer. Question number 5. A first order reaction has a rate constant 1.15 into 10 to the power of minus 3 per second. How long will 5 gram of this reactant take to reduce to 3 gram? This has appeared in the last year's question paper. So what is given? Rate constant is given, K. K is 1.15 into 10 to the power of minus 3 per second. How long will 5 gram of this reactant take to reduce to 3 gram? So R naught is initial concentration is 5 gram and the final concentration is 3 gram. So we need to find the time taken for 5 gram of reactant to reduce to 3 gram. So same formula, K equal to 2.303 by T log R naught by R, substituting the values for K, R naught and R. That is T equal to 2.303 divided by K value is 1.15 into 10 to the power of minus 3 log R naught is 5, R is 3. Log 5 by 3 is of the form log A by B can be written as log A minus log B. Similarly, we'll write this as log 5 minus log 3. Now using the log table, find the value of log 5 and log 3. Log 5 can be taken as log 50. Log 50 value is 0.6990. Similarly, log 30 can be written as the value of log 30 is 0.4771. Substituting these values here. See, log 5 is 0.6990 and log 3 is 0.4771. So we get the answer for T as 0.4438 into 10 to the power of 3 seconds, or T equal to 444 seconds. This is the answer. Question number 6. Calculate the half-life period of a first order reaction if the rate constant of the reaction is 6.93 into 10 to the power of minus 3 per second. We need to find the half-life, T of what is given, K. K is 6.93 into 10 to the power of minus 3. We know the formula to find the half-life of a first order reaction. That is T of is equal to 0.693 by K. Substituting the values, we get T of is equal to 0.693 divided by 6.93 into 10 to the power of minus 3. So on solving this, we get the answer as T of is equal to 100 seconds. This is the answer. Question number 7. Show that in a first order reaction, time required for completion of 99.9% is 10 times of half-life T of the reaction. We know the half-life of the first order reaction is given by T of is equal to 0.693 by K. Let us consider this as number 1, and time required for completion of 99.9% of the reaction. So if your initial concentration is 100, the final concentration remaining after completion of 99.9% is 100 minus 99.9 equal to 0.1. So this is your R naught, this is your R. Substituting the values of R naught and R, we get T equal to 2.303 by K log 100 by 0.1. So log 100 by 0.1 is log 10 to the power of 3. Log 10 to the power of 3 can be written as 3 log 10. So T equal to 2.303 by K into 3, and log of 10 is 1. So we get T equal to 6.909 by K. Let us put this as equation number 2. Now divide equation 2 by 1. That is T divided by T of 6.909 by K divided by 0.693 by K. So KK cancels. So remaining is this. So we get the answer as 9.96, which is approximately equal to 10. So T by T of is equal to 10, or the time required for completion of 99.9% is 10 times of half-life. Hence proved. This is the answer. Question number 8. The rate constant of a reaction is given by log K equal to 13.25 minus 1.28 into 10 to the power of 3 divided by T, K. Calculate the activation energy and pre-exponential factor. We know the Arrhenius equation K equal to A into e to the power of minus EA by RT. Now if you apply the log on both sides, this equation will take the form log K equal to log A minus EA divided by 2.303 RT. So using this formula, we can compare this formula with the given equation. So the given equation is log K equal to 13.25 minus 1.28 into 10 to the power of 3 divided by T. So we can see that comparing this 2 and 3, your log A is 13.25 and this minus EA by 2.303 RT equal to minus 1.28 into 10 to the power of 3 divided by T. Equating this, so this T and T will get cancelled. So EA divided by 2.303 R equal to 1.28 into 10 to the power of 3, or your activation energy EA equal to 24.50 into 10 to the power of 3 joule, or A equal to 24.50 kilojoule. So we got the activation energy. Now we'll find the pre-exponential factor, that is A. We need to find A. On comparing these two equations, now if you compare these two equations, your log A is 13.25. We need to find A. So log A equal to 13.25. A will be antilog of 13.25. So how to find antilog of 13.25? Whatever the number that comes before the decimal point will go as power, that is 10 to the power of 13. And we need to find the antilog of 25.25. So take the antilog page of logbook, and here 0.25, the antilog of 0.25 is 1778. And the decimal point should come after the first digit. So 1.778 into 10 to the power of 13. This is the pre-exponential factor. So we got the activation energy as EA equal to 24.50 kilojoules, and pre-exponential factor is A equal to 1.778 into 10 to the power of 13. This is the answer. Question number 9. In the given reaction, A is the reactant and B is the product. The rate constant K is, in the given reaction, the rate constant K is 2.0 into 10 to the power of minus 2 liter mole inverse seconds inverse. Find initial rate of reaction when A equal to 0.5 m at 298 Kelvin. So given, what is given? K, the rate constant is given as 2.0 into 10 to the power of minus 2. We need to find the initial rate of reaction. So when the formula for initial rate of reaction equal to rate equal to K into A to the power n. N is the order of the reaction. So here order of the reaction is 1, n equal to 1. We know the value of K. We know A, value of A is 0.5. So 2.0 into 10 to the power of minus 2 into A value is 0.5 and n is 1. So we get the answer for the rate as 1.0 into 10 to the power of minus 2. Liter mole inverse seconds inverse. This is the answer. Question number 9. Question number 9. This question has appeared in the model question paper of 2024-25. A reaction is first order in A and second order in B. Write the differential equation. The rate equation is given by K equal to A into K into A to the power of m and B to the power n, where m and n are the order of the reactions. Now here in this question, the reaction is first order in A means m becomes 1, and second order in B means n becomes 2. So write the differential rate equation. For the first question, this is the answer. How is the rate affected on increasing the concentration of B 3 times and decreasing the concentration of A by 2 times? So, increasing the concentration of B 3 times. So, we are increasing the concentration of B 3 times means 3B the whole square. And decreasing the concentration of A by 2 times, it is A half of A. On solving this, we get K into A by 2 into 3 square is 9, 9 into B square. So increasing B 3 times increases the rate by 9 times, and decreasing A by 2 times decreases the rate by half. So on solving this, we get this is half into 9, that is 9 by 2, which is equal to 4.5 times the original rate. Now the third question, how is the rate affected when the concentrations of both A and B are tripled, increased 3 times? When concentrations of A and B are tripled, rate equal to K into 3 times A to the power 1, because order of the reaction is 1, plus 3 times B, order of the reaction is 2, so we are squaring this. Now K into 3A plus 3 square is 9 into B square. So here this is 3 and here it is 9. So 3 into 9, the rate will be 27 times the original rate. This is the answer. If you find this video helpful, please don't forget to subscribe.